Welcome again to electrostatic field. Today we have a problem about the electrostatic potential. The problem statement is an electric charge is distributed uniformly along the negative y-axis in the free space with rho L equal to 1 over y squared plus 1 nanocoulomb per meter. Assuming the potential is 0 at infinity, find the potential at the 2 points B1, 0, 1, 0 and B2, 1, 0, 0. So let's plot this one first, this x, y, and z. And in the negative y-axis, we have the charge distributed over the y-axis, negative y-axis, with 1 over y2 y squared plus 1. We are being told to calculate at b1 0 1 0 and b2, which is here 1 0 and 0. To do so, we need to use the voltage equation which we have learned. This one, two things are missing, dl and r, because rho L is given. If we assume that we are taking element here dy, so our dl will be equal dy. Assume this point is 0 y 0. So for the first point, we calculate simply r equal to 0 minus 0, which will be 0, 1 minus y, this brings you 1 minus y in j direction, and 0 minus 0, it will bring you 0. And to calculate the magnitude, simply it will be 1 minus y. Substituting the equation, this will be our v equation, which we cannot solve directly. We need to do partial fraction. So to do the partial fraction is basically we have two terms. First power, so we can just simply use a constant here. This is the second power, then we need to use first power by plus c, multiply both sides by the denominator here. It will be reduced to this equation. Then we need to compare the coefficients. We have here a coefficient y of to the power 0 only. Otherwise, the two other coefficients are equal to 0. And if we look to the other side, y to 0, a multiplied by 1 here will bring you a here, and c multiplied by 1 here will bring you the second coefficient. Again, we don't have in the left hand side except of 0. Here we don't have any coefficient for y to the power of 1. Here by when multiplied by 1 will bring you a coefficient of y. Then you have your p. Y, c here multiplied by minus y bring you minus c. This ultimately brings you p equal to c. Likewise, the coefficient of y square we don't have here in the left hand side except 0. Here ay square, this bring you a here, and py multiplied by minus y bring you minus y. Ultimately, a will equal to b. Substituting in the first equation, this bring you a plus a, this one will be b, and c also can be represented as b. So ultimately, b equal to half. This means abc equal to half. Now we go back and substitute in our voltage equation. These halves are nothing but abc. Then we take this half as common, then this 4 become 8 here. Then ultimately we will find that we have three integration of 1 over 1 minus y, which is simply minus ln 1 minus y, and integration of y over y squared plus 1 dy. This one, if we multiply by 2 here, divided by half, then this one is derivative is here y. Then again, this is just half what is outside here, multiplied by ln y squared plus 1. Finally, the third term, which is 1 over y squared plus 1 dy, which is equal to simply 10 minus 1 y. Here I substituted with these values. Let's rewrite this term and later we'll understand why. This half can be used as exponent for what's inside the ln, like this. And also the two terms here can be rewritten as, because half, this one power, can be written as root of y squared plus 1. And then we have here minus 1 and two lns. If we have ln x minus ln y, this can be written as ln x over y. So this is what I have done here. And another way to write, if we divide here by y and here by y, then you get root of 1 plus 1 over y squared over 1 over y minus 1, and we understand why now. Now we substitute with the integral limits. Then you will have, if you substitute it for the ln term with 0, this one will reduce to 1. This also will reduce to 1. Then you have ln 1, which is nothing but 0. If you try to substitute with infinity, you will get infinity over infinity, which is not indefinite. But if you use this form here, you will find this is equal to ln 1 plus 1 over infinity under the root 1 over infinity minus 1, which means t just ln 1 again, which is 0. So at the end, this ln term will not bring except 0. Now, if we substitute it for time minus 1, you will have time minus 1, 0, and time minus 1 minus infinity. Time minus 1, 0 is nothing but 0. Time minus 1 infinity is minus pi over 2, and you have here minus, so you will get plus pi over 2. And just mathematical manipulation, then you will reach that V010 equal to 9 pi over 4. For the second point, again, we have the point of calculation 0, 1, 0. This is where our element exists, and we want to calculate at 1, 0, and 0. So 1 minus 1, this bring you 1i. 0 minus y bring you minus yj. If you take the magnitude, this will reduce to the root of 1 plus y squared. Substituting the voltage equation, luckily, this term and this term are the same, but this to the power of 1, this to the power of half. You can sum together the powers, and this reduced to y squared by plus 1 to the power of 3 over 2. You use tan alpha, the derivative both sides, this brings you dy, here the alpha, and the derivative of tan and is nothing but secant square. Last thing, you need to understand what is the new limits of the integrations at 1 minus infinity. If you substitute by infinity, this is nothing but alpha equal to by minus by over 2. And if you substitute by y equals 0, this bring you alpha equals 0. Then our integration will be rewritten as integration from minus pi over 2 to 0, secant square. Here you have tan square alpha plus 1. Tan square alpha plus 1 is nothing but secant square. This all reduce together and bring you with a cosine. Cosine is a very simple integration, which is nothing but sine, and substitute by the limits of integration from the minus pi over 2 to 0. Then you will have sine 0 and sine minus pi over 2. This is nothing but 0, and this bring you with minus 1, as you can see here. Finally, you do your mathematics, and finally you will reach that your V101 is equal to 9 volt. Thank you.